Hello students, this is the fourth session of this topic matrices. Today let me start with some of the important properties of algebraic operations of matrices, like commutative law, associative law, existence of identity, and existence of inverses, that is additive and multiplicative inverses. The word commutative means move or travel from one side to another side. The commutative law states that it can move numbers around and still arrive the same number. Is called commutative. Similarly, the associative law. The word associative is nothing but group, and it states that you can regroup the numbers, you will get the same number. Such law is called associative law. And the remaining two laws are called existence of additive and multiplicative identity and existence of additive and multiplicative inverse. Let me start with properties of addition of matrices. If capital A is equals to Aij, B is equals to Bij, and another matrix C is equals to Cij, where I and J stands for ith row and jth column, are three matrices of order m cross n. The order of the matrix is m cross n. Then we have the following laws. The first law, commutative law, defines matrix A plus B is always equal to B plus A. Just now I told you the commutative states that we can move matrices around and still we arrive the same matrix, or still we arrive a same number of matrix or the same answer is called a commutative law. For example, if A is a matrix added with another matrix B, if we move the matrix A and B and then we get B plus A, then A plus B is equals to B plus A. Such law is called a commutative law. Moving to the next matrix, that is properties of addition of matrices. The second law says associative law. To define the associative law, we should have three matrices: matrix A, matrix B, and matrix C. We write A plus B plus C is equal to A plus B plus C. Regrouping the terms, to the left hand side we group the first two, and to the right hand side we group the last two. Both the sides gives the same matrix. Such a law is called an associative law. Meaning, by regrouping the two matrices, we get a same matrix. Such law is called associative law. Next, existence of additive identity. Existence of additive identity. A zero matrix denoted by the notation 0 of order m cross n, same as the order of a matrix A, is additive identity. Zero matrix is called as an identity only if any matrix is added with a zero matrix or zero matrix is added with a given matrix, it gives a same matrix A, then zero matrix is always called an additive identity matrix. Likewise, existence of additive inverse. If A is any matrix, then minus A is called the inverse of a matrix A. If A is added with the negative of A, it gives zero matrix, or minus A is added with A, it gives a zero matrix, then minus A is called the inverse of A. Therefore, minus A is the additive inverse of A or negative of matrix A. Likewise, we have the properties of scalar multiplication. We have studied what is meant by scalar multiplication. Any real number can be multiplied to a given matrix. Such multiplication is called a scalar multiplication. In this case, we are going to study the properties of scalar multiplication. If A and B are matrices of order m cross n and K, K1 and K2 are any three real numbers, then we have first property, K into A plus B is always equals to Ka plus Kb. That is the another matrix. It is called Kb. Therefore, any real number can be multiplied to sum of any two matrices. Moving to the next property of a scalar multiplication. K1 plus K2 into matrix A, where K1 and K2 these are the real numbers. Then it can be represented by K1 into A plus K2 into A. Therefore, if any two real numbers are added and multiplied by A, then that can be written as K1A plus K2A. Similarly, 2 into matrix A, it can be represented by K1 to K2A, or this is equal to K2 into K1A. These are very elementary properties of scalar multiplication of a matrix. Finally, any real number can be multiplied to the given matrix, and that can be given by minus of K into A or K into minus of A. This is also called as negative of a matrix capital A. Properties of multiplication of matrices. If capital A and capital B, C are three matrices of order m cross n, then we have the commutative law, that is called matrix multiplication is what? You know how to find the matrix AB. That we know if the columns of matrix A is equal to the rows of matrix B, then AB exists. Similarly, the columns of matrix B is equal to the rows of matrix A are equal, BA exist. But in case of matrix multiplication, AB is never be equal to, or it is not equal to, BA. That's why in matrix multiplication, the commutative law does not holds good. That is, matrix multiplication is not commutative, or it is called non-commutative. Likewise, we can see the multiplication is associative or not. Let A, B and C are three matrices of the order m cross n. Then A into B into C is equal to A into B into C. As I told you, associative means grouping the matrices. If I group the first two to the left side and last two to the right hand side, then AB into C is always equal to A into BC. And such law is called as an associative law. Therefore, matrix multiplication is associative. Dear students, moving to the next properties of multiplication called distributive law. It is multiplication over addition. A is multiplied to the sum of any two matrices. Therefore, A into B plus C is always equals to AB plus AC, or A plus B into C is always equals to AC plus BC. Whenever both sides of equality are defined, such law is called a distributive law. Dear students, in the examination, 5-mark questions will be given either by associative law or distributive law. You can find these 5-mark questions in the part D section, question number 40 in the question paper. Next, existence of multiplicative matrix. For any square matrix or for any matrix capital A, there exists an identity matrix of same order such that I into A is equal to A into I is equal to A. Such multiplication is called existence of multiplicative identity, where I is an identity matrix of order of a matrix A. Therefore, here I is called multiplicative identity of a matrix A. Students, we will go to the next part called the transpose of a matrix. This is a question, important question for the one mark question in the exam. As transpose of a matrix. Let capital A be a matrix of order m cross n. Then n cross m is a matrix obtained by interchanging the rows and columns of a matrix A is called transpose of a matrix A, and it is denoted by the notation A dash or A to the power t. The transpose of a matrix is denoted by A dash or A to the power t. The meaning is interchanging the rows and columns of a matrix A is called transpose of a matrix A. For example, any matrix of any order, then its transpose A dash or A to the power t can be written as AGI. In the given matrix A, we have ith row and jth column and order is m cross n. Then its A dash is written as AJI, jth row, ith column, and the order of this matrix will be n cross m. Means in this case we are interchanging the rows and columns. For example, matrix A is equal to, the first row elements are, it is 2, 6, 11. Second row elements are 5, 9, 4. This is a matrix of order 2 cross 3. Then the transpose of this matrix is denoted by A to the power T is equal to the matrix. In this case, we have 2 rows and 3 columns. Interchanging the rows and columns, we'll get a new matrix of order 3 cross 2. Therefore, after applying the transpose of this matrix, we get A to the power T is equals to, the first row becomes a first column, 2, 6, 11. And the second row becomes a second column, 5, 9, 4. Such matrices is called a transpose of a matrix A. Another example, if capital A is equals to a matrix of order 3 cross 3. This matrix is of order 3 cross 3. The first row elements are 10, 3, 5. Second row elements are 7, 6, minus 7. And last row elements are minus 8, 4, 9. Then A to the power T can be written as, this matrix is also of order 3 cross 3. The transpose of A is also 3 cross 3 because same number of columns and rows are given here. Therefore, the transpose of this matrix is also of order 3 cross 3. The first row elements becomes first column, 10, 7, minus 8. Second row elements 3, 6, 4 becomes the second row, 3, 6, 4. The next column becomes, that is 5 minus 7, 9 becomes the next row of the A to the power T as 5 minus 7, 9. Such matrices are called the transpose of a matrix A and denoted by the notation A to the power T. Now let me start with transpose, that is properties of transpose of a matrix. If I take the double transpose of a given matrix, it gives a matrix A, that is A transpose to the power again a transpose. If you take 2 times of a transpose of a matrix A, that gives A, same matrix. Therefore, A to the power dash is always equals to A, or A to the power T always gives matrix A. For example, we have a matrix A in the second example as 10, 3, 5, 7, 6, minus 7, minus 8, 4, 9. The transpose of this matrix, first row elements are 10, 7, minus 8, 3, 6, 4 and 5, minus 9. If I take one more time the transpose of the above A dash, that gives a matrix again. Elements in the first row are 10, 7, minus 8. Second row elements are, column elements are 3, 6, 4 and last column elements are 5, minus 7 and 9. Therefore, A to the power T to the power T, that gives a matrix A. Now the another property, AB the whole dash is always equal to B dash A dash. And the second property is A plus B the whole dash is equal to A dash plus B dash. Next property is K into A the whole dash is always equals to K times A dash, or A into K dash is always equals to A dash into K. In general, A, B, C the whole dash is always equals to C dash, B dash into A dash. Next, symmetric and skew symmetric matrices. These are the important definitions for the exam point of view. In the examination, they may ask these definitions for 1 mark question. Define symmetric matrix or define a skew symmetric matrix. These are the expected questions in the examination for 1 mark. Let me start defining what is a symmetric matrix. A square matrix. To define a symmetricity or a skew symmetric matrix, we should know one should have a square matrix. Capital A, Aij, is said to be symmetric. This matrix A is said to be symmetric if the transpose of A is always equals to A. If transpose of A is always equal to A, then such matrices are called symmetric matrices. For example, if matrix A is equal to, we have the elements. This matrix is of order 3 cross 3. A is equal to root 3, 4, 1 in the first row. Second row elements are 4, 9, 6, and third row elements are 1, 6, minus 2. Let me take the transpose of the matrix A. The first row becomes the first column, root 3, 4, 1. Second row becomes the second column, which is 4, 9, 6. And third row becomes third column, 1, 6, minus 2. In this case, A dash is equals to A, or A to the power T is equals to A. For such matrix is called as a symmetric matrix. Therefore, in this case, A is symmetric. Define a skew symmetric matrix. Once again, matrix must be a square matrix. A square matrix A is said to be skew symmetric if A dash is equal to minus A. If A dash is equal to A, such matrix is called symmetric. But if A dash is equal to minus A, such matrices are called skew symmetric matrix. For example, if A is equals to, first row elements are 0, minus 5, 8. Second row elements are 5, 0, minus 9. And third row elements are minus 8, 9, 0. Therefore, the transpose of A denoted by the notation A raised to T or A to the power T or A dash. The first row becomes the first column. The row elements becomes the column 0, minus 5, 8. Second row becomes the second column, that is 5, 0, minus 9, 5, 0, minus 9. And third row becomes a third column, that is minus 8, 9, 0. Therefore, A to the power T is the transpose of A. But if we take the minus sign from A to the power T, that is A to the power T is equal to, if I take the negative sign from the given matrix A to the power T, we'll get an element minus of 0, minus 5, 8, plus 5, 0, minus 9, and minus 8, 9, 0. Therefore, A dash is equal to minus A. Such matrices are called a skew symmetric matrix. If A dash, A to the power T or A dash is equal to minus A, such matrices are called skew symmetric matrices. Students, in a skew symmetric matrix, the diagonal elements are all zeros. Diagonal elements are all zeros. And the non-diagonal elements are opposite in sign. 5, minus 5, minus 8, plus 8, 9, minus 9. In such cases, the matrix is always called a skew symmetric matrix. Therefore, in case of symmetricity, the definition goes A dash is equals to A, and in case of skew symmetricity, A dash is equals to minus A. Such matrices are called a symmetric and skew symmetric matrix. Here is a one note on symmetric and skew symmetricity. If A is a symmetric matrix, then Aij is always equals to Aji because of the definition of symmetricity. A dash is equals to A or A is equals to A dash. If A is a skew symmetric matrix, then Aij is always minus of Agi because of the definition of skew symmetricity. A dash is equal to minus A. Here is one important note. All diagonal elements of a skew symmetric matrix are zeros. Students, remember, in a skew symmetricity, all diagonal elements are zeros. Such matrix will be always called a skew symmetric matrix. Based on the symmetricity and skew symmetricity, we have one theorem, and which is important for the exam point of view in the examination. They may ask this question for 3 marks. I read the statement of the theorem. Is very important and easy. For any square matrix, as I told you, to define symmetricity and skew symmetricity, the matrix should be a square matrix with real entries. Then we have to prove that A plus A dash is symmetric, and also you have to prove that A minus A dash is skew symmetric. In this problem there are 2 questions. First thing is you have to prove A plus A dash is symmetric and A minus A dash is skew symmetric. Let me begin with, we have been given A is a square matrix. As we know, in case of addition of a matrices, if I add 2 matrices A plus B, we'll get another matrix. We can call it as either C or B. That matrix is also of the same order, A and B. With the help of this addition of 2 matrices, let me start proving this theorem. Let B is equals to, B is a new matrix obtained by addition of A and A dash. Then let me denote this as an equation number 1. To prove that A plus A dash is symmetric, let me take the transpose of the equation number 1 on both the sides. Therefore, B becomes B dash is equal to A plus A dash the whole dash. This is by taking transpose on both the sides. Then B dash as it is equal to, again by the note, or you can say by the properties, A plus B the whole dash is always equals to A dash plus B dash. By using these properties, we can write A dash plus A dash of dash, that gives A dash dash. Similarly, A dash as it is, as we know that A dash of dash is always equals to A, therefore this is equals to A. This can be written as A plus A dash or A dash plus A. But from equation number 1, our A plus A dash, from equation number 1, A plus A dash is always equals to what? B. Therefore, B dash is equals to B. This is the definition of a symmetric matrix. Therefore, B is nothing but A plus A dash and it is equal to B dash. Therefore, A plus A dash is always symmetric, or B is equals to A matrix. For this part, you will be given in the examination 1.5 mark. Similarly, with the definition of skew symmetricity, let me define the second part of this theorem. You have to prove that A minus A dash is a skew symmetric matrix. Let me start with, I will denote A minus A dash by the notation C, and let me denote by equation number 2. To define the symmetricity and skew symmetricity, we have to take the transpose of a matrix C, or the transpose of equation number 2. Therefore, C dash is equals to A minus A dash of dash. Again, by the definition or the properties of transpose of a matrix, that becomes A dash minus A dash of dash. Similarly, A dash remains same and A dash of dash is always equals to A. Therefore, C remains as it is, C dash remains as it is equal to, I'll take the minus sign from the above equation. Therefore, if I take a minus sign, plus A dash becomes minus A dash and minus A becomes plus A. Therefore, C dash is equal to, this minus sign remains the same, and from equation number 2, A minus A dash is equal to, it is C. Therefore, once again we can see that C dash is always equals to minus C. It satisfies the skew symmetricity definition. Therefore, C is equals to A minus A dash is always a skew symmetric matrix. Therefore, the students, you remember A plus A dash is always symmetric and A minus A dash is always skew symmetric matrix. For second part of this theorem will be given 1.5 mark. For the first part of the theorem will be given 1.5 mark. In all, the question will be asked in the examination for 3 marks. Now moving to the second theorem of the matrices. Any matrix which is a square can be expressed as sum of a symmetric and skew symmetric matrix. In the first session only I told you the 3 mark questions will be asked, either problems or theorems on symmetric and skew symmetricity. Now in this case, this proof is not important for the exam point of view. Only for understanding I will sketch the proof, but the problems will be asked in the examination for 3 marks. Let me begin with the proof. Let A be any square matrix, then we can write capital A is equals to A plus A dash plus A minus A dash. As we know, A plus A dash is symmetric and A minus A dash is skew symmetric. If I add the symmetric and skew symmetric matrix, A dash and A dash will cancelled, we'll get 2A. But we have to show that it is equals to A. But here A is equals to 2A, which is not correct. For that sake of simplicity, we can write capital A is equal to 1 by 2 times A plus A dash and plus 1 by 2 times A minus A dash. As we know, 1 by 2 times A plus A dash is also symmetric and 1 by 2 times A minus A dash is also skew symmetric. Therefore, the sum of these two gives 2A into 1 by 2. 2 cancels, it gives A is equals to A. Therefore, any matrix can be written as the sum of symmetric and skew symmetric matrix. Or we can say that the algebraic sum of 1 by 2 times A plus A dash plus 1 by 2 times A minus A dash. Dear students, as I told you, the scope for the proof in the examination is not important of this theorem. That's why only the problems can be told in the examination. We can remember this formula. Before I conclude my session, dear students, in the last session I have given few examples for assignment in the first 3 slides. The first slide, question number 4, sub question 3, its answer is capital A is equals to, the first row elements are 2, 9 by 2, second row elements are 9 by 2, 8. Likewise, in the second slide, question number 5, sub question number 2, the answer for that sub question number 2 is capital A is equals to, first row elements are 1, 1 by 2, 0, 5 by 2, 2, 3 by 2, and 4, 7 by 2, 3. Again, the question number 5 with the sub question 3, capital A is equals to, the first row elements are 2, 9 by 2, 8, 9 by 2, 8, 25 by 2 in the second row, and third row elements are 8, 25 by 2, 18. Finally, there is one more question in the third slide is given to you. Question number 6, sub question 2, the answer for this matrix is, here it is given 2, 9 by 2, 8 and 25 by 2. Second row elements are 9 by 2, 8, 25 by 2, 18, and the last row elements are 8, 25 by 2, 18 and 14. Students, you can cross verify your answers from this slide. With this, I conclude my today's session. I thank for watching this video. For any queries, contact the given number. Thank you once again. Stay home, stay safe.